All right. So, parallel and perpendicular lines. We're going to keep moving on. We've been talking about how if lines are parallel, what does that mean? And if we have other things, what other things can we do to make sure that we have lines parallel? Now we're just going to get into, working with parallel and perpendicular lines. Starting with this here, with our kickoff from last time. Now, what's missing is the measure, my marker works, measure of angle 6 equals 2x plus 6. Should be with that. Now, if we look at 2 and 6 are going to be corresponding angles. And we know corresponding angles are congruent. So we're going to set 40 equal to 2x plus 6. And if we do our algebra with that, we'd end up with 34 equaling 2x. So in other words, x is 17. Okay. So theorem 3.9 first, I should say. Theorem 3.9. Slide this over and get this right. All right. So theorem 3.9. Two lines are going to be parallel to the same line. Then that means that they're going to be parallel to each other. So if we have A parallel to B and B parallel to C, then we know that A and C are going to be parallel as well. All right. Theorem 3.10. In a plane, if two lines are perpendicular to the same line, then we know that they're going to be parallel to each other. So T cutting through here is perpendicular to M and perpendicular to N. Therefore, M and N will be parallel to each other. And we're going to prove that. So we can do this in 3 steps. Okay. So first step, always are given. So R perpendicular to T. This upside down T means perpendicular. And the reason why is given. So knowing those are perpendicular to each other, well, we know then that angles 1 is going to be congruent to angle 2 by definition. And we're saying by definition because we know that if they're perpendicular, then we know those are 90-degree angles. So definition of 90-degree angles, or definition of perpendicular, but also definition of congruent, we know they're the same measure. And I'm off the page, sorry. So, knowing that 1 and 2 are congruent, that's going to roll right into our proof saying R is parallel to S. Because if we know that 1 and 2 are congruent, 1 and 2 are going to end up being corresponding angles. And so postulate 3-2 says that if the corresponding angles are congruent, then we know the lines are parallel. So, 3-step problem. If you think about it here, we were given the first 2 things here. We were given our third thing. We just found out 3 of them. So we found out half of it. Half of it was just given to us if you follow those right things. All right. And if I could turn my page. So to make a frame for a painting, a miter box and backs are used to cut the framing at 45 degrees. If you don't know what a miter box is, it's what they used before we had miter saws, where it had little grooves in it was a wood box that had little grooves in it, so you could cut certain angles out of wood. Now we just have a miter saw that we can turn to whatever angle we want and make those cuts. But that's what they're using here. So we want to make these 45 degrees cuts, explain why cutting them at this angle ensures that the opposite sides of the framing will be parallel. So if we look at our board, they're going to cut it like this. So that this here is 45 degrees and this over here is 45 degrees. So they're going to cut all those boards like that. So then they're going to fit together like this. So this here is also 45 and cutting in like that. So our 45 cuts match up so that these fit in like so. So why are these? Well, 45 and 45 make these 90s. So each corner is going to be 90, and they're going to be 90 to the same thing, which is this bottom board. So by that theorem, 310, we're going to be parallel those opposite sides, because 310 says if they're perpendicular to the same line, they're parallel to each other. Okay. Next, theorem 311, which, if you don't know, is a great band. Just saying. In a plane, if a line is perpendicular to one of two parallel lines, then it also is perpendicular to the other line. So if we're dealing with parallel lines, we have one line that's perpendicular to the other one, then our other parallel line is going to be perpendicular to it as well. So it's kind of a back way to Theorem 310, kind of a converse, but not quite. So if we have our proof here, which again, we're going to be able to do in 3 steps. So number 1 is our given. Now, the nice thing on quizzes and tests, if it's really big like this, you can circle this one and arrow it down and say, hey, this is going to go right here. And again, we're going to be able to do this in 3 steps. So this last one here, A perpendicular to D. So what do we know? Well, we know that A and B are perpendicular and B and C are perpendicular. So A and B, B and C. So they're both perpendicular to each other. So that means A is going to be parallel to C by that Theorem 310 that we just got done doing a little bit ago. Now, we're actually not proving Theorem 311, and so that's what's going to allow us to do this. But the reason why AD, so if we continued A down here, this would be perpendicular as well by that Theorem 311. So this isn't proving Theorem 311, but it's just doing a proof using these here. And so we can make this work thanks to Theorem 311. And that is it. That is this lesson. So let me know if you have any questions. Otherwise, until next time, we'll talk to you later.